One of the most important concepts in organic is the reaction between a nucleophile and an electrophile. A nucleophile is an electron source. Nucleophiles can either be strong nucleophiles or they can be weak nucleophiles. But whether they are strong or weak, they need to have lone pairs in there. So this is a sign where you can identify where is your nucleophile. Nucleophiles, they do give electrons to electrophiles or species that lack electrons. So the electrophile needs to have either a solid positive charge or it needs to be a partial positive that is created due to the direction of polarization. In this case, what you're making is a covalent bond between the nucleophile and the electrophile. So that is a chemical reaction. Let's have an example. Label the following electrophile and the nucleophile sites in each molecule. So in order to do this, what you need to do is look at your electronegative element and look at the carbons that are connected to it. And then do the direction of polarization in there, just for you to know which or where is the flow of electrons. The flow of electrons is going from the sp3 hybrid carbons to the oxygen. So these two carbons here are going to be an electrophile, and the oxygen is going to be the electron rich. This is going to be the nucleophile. This is the dipole in this case, or the direction of polarization or the motion of electrons. So the electrophile is going to be the carbons, and the nucleophile is going to be the oxygen. Same thing over here, bromine. Bromine is the source of electrons, right? So the bromine is going to be the nucleophilic site. And then the electrophilic site here is going to be the carbon because this carbon is directly connected to the bromine. So you will have a direction of polarization or the motion of electrons between the carbon and the bromine, making this carbon partial positive and the bromine is going to be partial negative. This is how the flow of electron is going. So this is going to be your electrophile. Let's go ahead and label that. So this is going to be the E plus and the bromine is going to be the nucleophile. Remember that the reaction always happens between nucleophiles and electrophiles. Here in this example, we are locating the nucleophile and the electrophile in the same molecule. This doesn't mean that they are doing reaction with each other, but we are just labeling the sites in the molecule. Same thing over here. I do have my lone pair. This is a negative charge and the lone pair. This is a nucleophilic site. The moment you see lone pairs, then this is definitely a nucleophile in this case. And double bonds are also nucleophiles. Remember, double bonds, they are the overlap of two p orbitals in there, and each p orbital has one electron. So if the pi bond is broken, then in this case, you will release those two electrons. So it's going to be a source of electrons in there. So the double bond is a nucleophile, the oxygen is a nucleophile, and this carbon is a nucleophile. Now, the electrophile is the carbon that is connected to the oxygen. So here I do have this carbon, it's connected to the oxygen. This is the direction of polarization, so it's going to be a partial positive. So the this carbon here is going to be my E plus, the electrophile in there. Same thing, this is the carbon that is connected to the electronegative element, the carbon that is connected to the electronegative element. So this carbon is going to be partial positive, and this one is going to be partial positive. The sulfur is going to be partial negative, so the sulfur is going to be my nucleophile. And both of these carbons, so this carbon here and this carbon there, both are going to be my electrophile. Also, the double bond is going to be a nucleophile as well. Here, the oxygen is the nucleophile. Look for the lone pairs. This oxygen also is going to be a nucleophile. And this carbon over here, because it's an sp2 hybrid carbon, this carbon is an sp3 hybrid carbon. So there's a difference between an sp2 and an sp3 because the sp2 is more electronegative. So this carbon is going to be more partial positive. It's going to lose more electrons towards this oxygen. So it's going to be more partial positive. So this carbon over here is going to be the electrophile. This carbon is not going to be an electrophile compared to this carbon. Okay, let's see. So again, this is the direction of polarization. Put your lone pairs, please. So this oxygen is going to be a nucleophile. This oxygen is a nucleophile. And this oxygen is a nucleophile. You are introducing a direction of polarization. So this carbon is going to be my E plus. This is partial positive. And this carbon is going to be partial positive as well. So it's going to be the E plus. Structural isomers are isomers that have the same molecular formula, but different connectivities of atoms. So we've learned how to draw structural isomers for alkanes. Let's go ahead and do it for different functional groups. Let's have an example. So let's draw the structural isomers for C3H6O. The first thing that you do is do the DBE. And the DBE is the number of carbons times 2 plus 2 minus the number of hydrogens divided by 2. Okay? Don't forget that if you have a nitrogen, you need to subtract it from the number of hydrogens. If you have a halogen, you need to add it to the hydrogens. You neglect the oxygen, the phosphorus, and the sulfur. And that is going to make the DBE here to be equal to 1. Normally, whenever I have a DBE equal to 1 and I have an oxygen in my molecular formula, this means that I'm going to end up getting a carbonyl as one of the possibilities for the degree of unsaturation because I know that a double bond is a DBE of 1. I can also have a double bond, an alkene in there. So I can also have an alkene. If I have an alkene, then the oxygen in there is going to be in a form of an OH or an ether. Or I can have a cycle because any one of those, a double bond, whether in a form of a carbonyl or a double bond, whether in a form of an alkene or a cycle, any one of those is going to be a DBE of 1. So let's start with all the structures of the carbonyls first. We have two types of carbonyls, aldehydes and ketones in there. I have 3 carbons, so we're going to go ahead and do 1, 2, and the 3 carbons. The last carbon, I'm going to make it an aldehyde. Okay, so this is my aldehyde structure, or I can put the carbonyl in the middle and make that a ketone. So this is an aldehyde. This is a ketone. I cannot make any other aldehydes and ketones out of C3H6. So I need to move along now with the double bond. I still have 3 carbons in there. Here you go. So these are my 3 carbons. Now, I didn't count the number of hydrogens in there because definitely when I have the number of carbons right, the number of oxygens right, definitely the number of hydrogens should match. So this is a 3 hydrogens, 2 hydrogens, and a hydrogen. That's going to make it as a 6. In this one over here, I have 3 hydrogens on both sides as well. So for the double bond, let's go ahead and put the double bond in here. If we put the double bond in here, we've used the 3 carbons. I still have 3 carbons, and see how many hydrogens I used. I used the 3 hydrogens here. A hydrogen in there, this is 4. So I need to have 2 hydrogens left. To have 2 hydrogens left and an oxygen, I would need to have an OH in there. I know that this is a hydrogen, but you don't have to write it because it is a skeletal form. So this is going to be an OH. I can have my double bond on carbon number 1. This is 2, this is 3. So I can have the OH on carbon number 1. I can change the connectivity of the OH, keep the double bond still on carbon number 1, but I can have the OH on carbon number 2. So this is 1 and this is 2 in there. Okay. You can easily see the difference between those two. They carry the same molecular formula C3H6O, but the connectivity of the atoms is different. The OH here is connected to carbon number 1. Here the OH is connected to carbon number 2. I'm done from my alcohol isomers. Now I'm going to go ahead and draw the ether isomers in there. So I can have my alkene. Okay, I need 3 carbons and an oxygen. I know that ether has a formula of an ROR. So I need to arrange the carbons around the oxygen there. So I'm going to put 2 carbons on one end and 1 carbon on the other. This is going to be the only ether that I can go ahead and draw. In this case, let's count the number of hydrogens. I have 1, 2, 3, 4, 5, and 6. So I have 6 hydrogens in there. So these are the alcohol isomers. And this is the ether isomer. And notice that all of these isomers, whether they are aldehydes, ketones, or alcohols or ethers, they have one double bond of unsaturation. The DBE is equal to 1 there. Now, I'm done from the alcohol. I'm done from the ether in there. I'm done from the double bond. Now let's go ahead and do the cycle. For the cycle, I can have a cycle of, since it's a 3 carbons, the smallest carbon cycle I can form is a 3 carbons in there. Then I'm going to end up with an O and an H from my molecular formula. So I've used the 3 carbons in there. I've used 1, 2, 3, 4, 5 hydrogens, so I'm left with 1. So this is why it needs to be an OH. I can make an epoxide as well. If I make an epoxide, I will be short of a CH3, so I can put the CH3 on this carbon. I can also make a cycle of 4-membered rings. In this case, let's count the number of hydrogens. This is 1, 2, 3, 4, and 5, and 6. So I have my 6 hydrogens, my 3 carbons, and my oxygen. Pretty much these are all my choices, all the isomers in there that have a DBE of 1 for C3H6O. When do you know when to stop? Well, there is no rule in there, because once you do the DBE, you have to put your choices that you are using. So if you're using a carbonyl, and this means that you need to draw all the aldehydes and the ketone, especially because you have 1 oxygen in there. This is why we said it's an aldehyde and a ketone. I need to make use of the oxygen after I'm done from the carbonyl. If I have a double bond, then I know that it's going to be an alcohol or an ether. And ethers exist as a chain. Because I do have a DBE of 1, I can add my double bond. Or if I don't want to add my double bond, then I need to use the cycle in there in order to incorporate the oxygen. Let's have another example. C3, H8, and an O. Do the DBE. It's the number of carbons times 2 plus 2 minus the number of hydrogens divided by 2. This is going to be a 0. 0 means that there is no double bonds, there is no cycle. But I have an oxygen in my formula. So if I have an oxygen in my formula and I have a 0 DBE, this means 2 things. I'm going to have either an alcohol or I'm going to have an ether. The alcohol has a general formula of ROH and the ether has a formula of ROR. Always put the general formula in there just to know the connectivity. So let's start with the alcohols. I have 3 carbons. So this is 1, this is 2, this is 3. I'm just going to put the OH at the end. I can also move the OH along and put it on the second carbon. It makes it easy if you go ahead and number your carbons. You can start numbering on any side you want, on the right or on the left. We're not naming in here, so it really doesn't matter. But just be consistent. So if you start numbering from the right, just be consistent for all your structures in there. These are the only two alcohol isomers that I could write for C3H8O. I don't have any other choices. Now for the ether, um, I'm gonna put two carbons on one end and one carbon on the other, and pretty much that's it. This is my only ether that is drawn for this molecular formula. So I'm going to end up getting three different isomers in there. Let's have another example, C3H5N. Now in this example, I do have nitrogen in my molecular formula. So when you do the DBE, please subtract the number of nitrogens from the number of hydrogens. So I will have a total of four in this case for the number of hydrogens. So it's the number of carbons times 2 plus 2 minus the number of hydrogens. Now it is 4 divided by 2. So the answer is 2. When your DBE is equal to 2 and you have a nitrogen in your molecular formula, this means that you have a triple bond and specifically you have a cyanide. Okay? So especially because you have that low number of carbons in there and you want to fit a DBE of 2, you cannot have two double bonds in there that are adjacent to each other. The structure will not be stable. So this is why you will end up having a triple bond instead. So let's go ahead and draw the structure. Since I have a nitrogen in there, I can have either a C triple bond N, or I can have an amine. And the only amine that I can have with a triple bond is going to be the NH2. Let's go ahead and see if we can arrange something else. Let's do the triple bond first. So we're going to have 1, 2, 3. So these are my 3 carbons in there. And then my triple bond, and then the nitrogen. So this is going to be my cyanide in there. Please guys pay attention that this needs to be linear. This part needs to be linear. So let's count the number of hydrogens. This is 3, 4, 5. Pretty much that's it. So I have 3 hydrogens here, 2 hydrogens there. I am done from the number of hydrogens. Okay, so let's see. If we start with a triple bond, so far I've used 2 carbons. I still need one more. So if this is CH2 and then if it's an NH2, see, it has to be NH2 in there. I cannot do a secondary or a tertiary amine. It has to be a primary amine in this case. Because this is what's left, a nitrogen and 2 hydrogens after I put a carbon in there. So this is going to be my another isomer is the second isomer can be a triple bond connected to a CH2. So far I've used a carbon here, a carbon here. So this is a carbon, a CH2, and then an NH2. Still pay attention, this is linear. Okay, so these are my 3 carbons in there. Let's see. This is going to be 1 and 2 hydrogens here. I have a hydrogen there. I have 2 hydrogens here. And I have 2 hydrogens there. This is going to total my 5 hydrogens. I can also put a triple bond. And on one side, I can put the NH2. And on the other side, I can put my carbon. In this case, I have a carbon, 2 carbons, and 3 carbons in there. And all of them need to be linear in this case. So there are three isomers for C3H5